Welcome. Today, we're digging into a really remarkable piece of work. He doesn't just talk about sustainable energy, it actually puts numbers on it.
Right. We're looking at David MacKay's book, Sustainable Energy Without the Hot Air. It's kind of famous for using arithmetic, plain old maths, to cut through the usual debates.
Yeah, exactly. He wanted to get past what he called quantal, all those vague words like huge or massive that get thrown around.
His whole point was simple, really. Sustainable energy. It's an engineering challenge, so you need numbers, not nice-sounding adjectives.
So our mission is to follow his approach. We want to look really hard at whether our modern affluent lifestyle, the way we live, can actually be powered just by sustainable energy sources found within a country, using the UK as a specific example because it's, densely populated.
And it's not about feelings or politics, at least not at first. It's just about the physics, the raw numbers. Can it even work on paper?
And you see straight away why this is so important when you look at how polarized the discussion usually is. MacKay pointed this out, didn't he?
Oh, definitely. He highlighted people like Michael Meacher saying, we can only do this with renewables. And then Sir Bernard Ingham saying the exact opposite, that relying only on renewables is, quote, living in an utter dream world.
Right, total opposites. That kind of back and forth just generates heat, not light.
Exactly. So MacKay's approach was basically, okay, everyone, stop shouting. Let's just calculate. And the beauty of it is the maths involved isn't, super advanced physics.
No, he made it accessible for policymakers, for students, for anyone really who's willing to sit down and actually look at the figures.
But to do that, to compare apples with apples, you need a common language. You can't be jumping between terawatt hours and exajoules and, barrels of oil equivalent.
It's too confusing. Nobody intuitively gets those scales.
Right. So MacKay came up with this single human scale unit, the kilowatt hour per day per person, KOEHD.
And the way he framed it is brilliant, that analogy he used.
The energy servant analogy. Yeah, it's powerful. 1 kilowatt is roughly the power you'd get from one person working for you nonstop, 204/7.
So if your lifestyle uses a 200 kilowatt rater,
that's like having 200 invisible servants working constantly just for you.
Yeah.
Suddenly, our energy use feels much more tangible, much more personal.
It really does. And just to keep the numbers handy for everyone listening, 1 kilowatt of continuous power is 24 kilowatt ratio. And about 40 watts running all the time, that's roughly 1 kilowatt ratio.
Okay, so with that unit in mind, we get to the core of his method, the balance sheet. 2 columns.
Left column, consumption, what we actually use. Right column, production, what we can conceivably, sustainably generate ourselves.
And the crucial first step, MacKay insisted, is just asking, can the right column physically match the left? Forget cost, forget politics for a moment. Does the maths even add up?
Because if the physics says no, then arguing about economics is pointless.
Exactly. Physics first.
Okay, so let's start building that left column. How much energy does our modern life actually demand?
Well, the national averages are already quite eye-opening. The typical European uses somewhere around 125 kilowatts per person.
But that's just the average. If you're talking about someone living a, let's say, typically affluent life, drives a car, maybe flies once a year, heats a decent-sized home, buys imported stuff.
Yeah, then that number climbs easily towards 200 kilowatt-hours. And in the U.S., the average is even higher, closer to 300 kilowatt-hours.
300 energy servants. Wow.
It's a lot. So MacKay simplifies things a bit with his cartoon Britain model, just focusing on the big hitters to make the conversation easier.
Right. So what are the big parts of that cartoon?
He breaks it down roughly. 40 kilowatt-hours for heating our homes and buildings, another 40 kilowatt-hours for transport, and then about 45 kilowatt-hours worth of fuel gas, coal needed to generate the electricity we use, which comes out as about 18 kilowatt-hours per day of actual electricity at the plug.
Okay, so even that simplified picture gets us close to that 125 kilowatt average, and that's before we count all the energy hidden in the things we buy.
Exactly. And when you dig into those categories, transport really jumps out. If you add up daily driving, moving goods around, maybe that occasional flight.
It can easily hit 70 kilowatt a day or even more per person. It's the real guzzler in an affluent lifestyle.
Let's zoom in on driving a car. MacKay uses that 40 kilowatt figure as a benchmark for the UK average driver.
Okay. And what about saving energy there? We hear a lot about efficiency.
Well, yes, but one of the biggest savings is often overlooked because it's about behavior, not just tech.
You mean driving slower?
Exactly. It's basic physics, but the effect is massive. Energy use doesn't just drop a bit when you slow down. MacKay shows that if you have your speed, say, go from 70 miles per hour down to 35 miles per hour for the same amount of time driving, your energy consumption drops by a factor of 8.
8 times less energy just from slowing down.
Yeah, because air resistance increases with the square speed, and the power needed to overcome it goes up with the cube of speed. It's a huge lever we often ignore.
Okay, that's significant. What about electric cars then? That's the big technological fix we hear about.
EVs definitely offer big efficiency gains, even using today's electricity mix. A smaller EV, something like an IEV or maybe a GWIZ back then, might use only 10 to 20 kilowatts of electricity to go 100 kilometers.
Which sounds much better than burning petrol. But what if the electricity comes from, say, a gas power plant?
That's the key comparison MacKay makes. Even if you factor in the emissions from generating that electricity with the typical fossil fuel mix, the effective CO2 emissions of the EV come out around 100 grams per kilometer.
And how does that compare?
That's right down there with the absolute best, most fuel-efficient petrol or diesel cars you could buy. So switching to an EV is a major win now, and it gets even better as the grid gets cleaner.
Right. But then there's flying. That annual holiday flight. I remember seeing this figure in the book, and it's just staggering.
It is. Taking just one typical long-haul intercontinental trip per year, say London to New York and back, adds a whopping 30 kilowatt-hours to your average daily consumption over the whole year.
30 kilowatt-hours a day.
Yep.
Just for one trip. That's nearly as much as heating your house.
Pretty much. Think about it, that one choice means you need 30 extra energy servants working for you every single day, all year round. It often gets missed in those standard carbon footprint calculations, too.
So one flight basically wipes out savings from months of careful recycling or shorter showers. It really shows what the big changes are versus the small stuff.
It does. Though, to be fair, MacKay adds some context. He points out that a full jumbo jet, like a 747, is actually pretty efficient per person per kilometer. Maybe twice as efficient as driving alone in a car. The issue isn't so much the plane itself, it's the incredible distances we travel, the high speeds, and the fact that right now we don't really have a workable, non-fossil fuel alternative for long flights.
Right. Okay, so from speed to heat. Heating and cooling, that's another big slice, about 38 to 40 kilowatt-hours, you said. Mostly burning gas or oil for lower grade heat.
Yeah, and this is where building design, insulation, and behavior all come together. Improving insulation in older houses is obviously crucial. But again, simple actions have a big impact.
Like turn down the thermostat.
Exactly. Just turning it down from, say, 20 degrees Celsius, which is pretty standard, to 17 degrees Celsius can cut heating demand by 30%. That's potentially saving 12 kilowatts right there. Huge win for just putting on a jumper.
Okay. And what about technologies like CHP, combined heat and power? They sound efficient.
They do sound good on paper to generate electricity and use the waste heat. But MacKay threw a bit of cold water on them, didn't he?
He did. What was the main issue?
The big problem is inflexibility. CHP systems are most efficient when you need both the heat and the electricity they produce in the ratio they produce it. But our demand for heat and power rarely lines up perfectly like that.
Right. So in summer, you might still need the electricity, but not the heat.
Precisely. So you either waste the heat or you run the system inefficiently just for the power, which means compared to just using a modern, super efficient condensing boiler for heat and getting power from the grid, the actual overall energy saving from CHP is often quite small, maybe only 10% better, not the huge gains sometimes claimed.
Okay. So we've done the obvious stuff, transport, heating. What about the hidden energy costs, the stuff we buy, our food?
Right, the embedded energy. This is crucial. Official national energy figures often don't count the energy used to make all the things we import.
So MacKay tried to estimate that?
Yeah, he looked at the sheer weight of manufactured goods coming into the UK. The metals, the plastics, the electronics, the cars. And his calculation was that just making that imported stuff requires at least another 41 kilowatt-hour per person.
41? Just for imported goods?
At least. Add in energy for manufacturing things within the UK, plus about 12 kilowatt-hours just for transporting all those goods around. The total energy footprint of stuff ends up being well over 60 kilowatt-hours.
That's enormous. That's almost as much as heating. It's completely hidden usually.
Totally hidden. And then there's the energy needed to feed us. The whole food chain. For a typical mixed diet veg, dairy, meat, eggs, it takes about 12 kilowatt-hours of energy input into farming and processing.
And he broke that down too, didn't he? The milk and eggs example.
Yeah, it's quite vivid. Having a pint of milk and 50 grams of cheese each day requires, energetically speaking, running about 1/16 of a dairy cow continuously. That's about 1.5 kilowatt-hour HE. And eating 2 eggs a day needs about 1 kilowatt-hour of energy dedicated to the poultry part of the food chain.
This kind of detail really shows where personal choices do make a difference beyond just tiny saving.
Absolutely. He suggested, for instance, that choosing to eat vegetarian 6 days a week could save you around 10 kilowatt hour HE. That's a proper chunk out of your total, comparable to insulating your loft.
Okay, now speaking of tiny savings,
Yeah.
we have to talk about the phone charger myth.
We've all heard it constantly from campaigns, even government advice. Unplug your chargers to save the planet.
So what did the numbers actually say?
The numbers are just brutal. A modern phone charger left plugged in but idle, and they're incredibly efficient now, uses maybe zero point 0.3 watts.
Okay, zero point 0.3 watts. How much is that in our daily unit?
It translates to about 0.01 kilowatt, 1/100th of a kilowatt hour per day.
0.01. When we're talking about a total consumption of maybe 200 kilowatt hour wart.
Exactly. Unplugging your phone charger saves less than 1/100th of 1% of an affluent person's energy use. It's completely, utterly negligible in the grand scheme of things.
It's the absolute definition of what he called bailing the Titanic with a tea strainer.
Precisely. And the serious point is, focusing attention and effort on these tiny things distracts from the real levers, the driving, the flying, the heating. MacKay's relentless focus on numbers forces us to see that distinction. Don't waste time on the tea strainer.
Right, so we've got a target number for consumption, let's say around 200 kilowatt hour for an affluent lifestyle. Now, the big question, can we actually generate that much sustainably from within a country like the UK? Let's fill the right column.
And this is where the physical constraints really bite, especially land area. The UK is densely populated, only about 4,000 square meters per person. That limits everything.
Okay, so let's start with onshore wind. What did MacKay calculate as the maximum plausible output?
His maximum plausible figure was 20 kilowatt per person.
20. Okay, it's something. But what does it take to get that?
To achieve that 20 kilowatt, you'd need to cover 10% of the absolute windiest land in the UK with turbines. We're talking about huge swaths of land operating at a power density of about 2 watts per square meter.
10% of the windiest land. What does that look like globally?
In terms of sheer number of turbines, getting that 20 kilowatt rate for the UK would have required installing double the entire world's wind turbine fleet back when he did the calculations around 2006.
Double the world's capacity just for the UK.
Yep. So it's huge in effort and scale, but the output, 20 kilowatt rate, is still only half the energy needed just to drive a typical car 50 kilometers a day. The numbers just don't support wind power solving everything on its own.
Okay, what about solar? We've got rooftops and potential for solar farms.
Solar thermal for heating water is quite practical. If you covered all suitable south-facing roofs, maybe 10 square meters per person with thermal panels, you could get a decent 10 kilowatt rate of heat energy. That's useful.
But for electricity generation, PV panels, you need more space.
A lot more space. MacKay did a kind of thought experiment. What if you covered 10% of the entire UK land area with 10% efficient PV panels? That could theoretically yield 50 kilowatt per person. But
covering 10% of the country, farmland, parks, everything with solar panels.
exactly, it's completely implausible, politically impossible, ecologically questionable, and at the time, the electricity cost would have been about 4 times the market rate. Plus, it would have required installing over 100 times the world's entire PV capacity back then. The land density problem just kills large-scale PV in a country like the UK.
Right, and that density problem is even worse for biofuels or biomass, isn't it? Growing plants for energy.
It's incredibly land hungry. MacKay's absolute top-end, extremely optimistic estimate was this. If you took 75% of the UK's land, basically, most of the farmland currently used for food, and switched it to growing energy crops,
Okay, what would you get?
you might get 24 kilowatts per person. And that's before accounting for energy losses and farming and processing and, the minor issue of not having enough land left to feed people.
He had that devastating historical comparison too.
Yeah, the Middle Ages point. Back then, with much lower energy use, maybe 8 kilowatts per person, people needed about 10,000 square meters of land each, mostly woodland, just to survive sustainably using biomass.
And today in the UK, we only have 4,000 square meters per person.
So even if we reduced our energy needs back to medieval levels, we still wouldn't have enough land to power ourselves just with biomass grown here. Population density is the killer constraint.
So land-based options are severely limited. We have to look offshore.
To the seas, yeah. Offshore wind avoids some of the visual impact issues, but it's more expensive.
How did MacKay break that down?
He split it into shallow and deep. Shallow offshore wind in waters less than 30 meters deep is technically feasible and economically more viable. He estimated a plausible contribution of about 16 kilowatts per person from that.
Okay, 16, that's a solid chunk.
It is, but to get really big numbers, you have to go into deeper water, further offshore.
And the potential there.
Deep offshore wind could potentially add another 32 kilowatt IRTs. But the scale is immense. We're talking about filling an area of sea 30% bigger than the entire country of Wales with giant turbines, using technology that was and still is very challenging and costly. It's a major industrialization of the marine environment.
Right. And there's harnessing tides and waves directly.
Tidal power has potential. Using barrages across estuaries, underwater turbines, and tidal streams or lagoons, the maximum physical potential might be around 14 kilowatt IRTs. Wave power is much harder to harness reliably, maybe 4 kilowatt at most.
So adding those up, 14 plus 4, another 18 kilowatt array maybe? Respectable, but again, we're adding single digits or low double digits to a target of 200.
Exactly. We've tallied up wind, solar, biomass, hydro, tide, wave, all the main renewables, and even being incredibly optimistic, incredibly ambitious.
We're nowhere near the 200 kilowatt work for consumption, are we?
Not even close. Which forces us to look at the non-renewable options that could provide power sustainably over very long timescales.
Which brings us to nuclear fission.
Right. But MacKay draws a really important line here. Standard nuclear power today, the kind that uses uranium fuel once and then treats most of it as waste, that's not sustainable in the long run. The easily mined uranium will run out.
So how much could current tech provide sustainably?
From conventional uranium reserves used in today's reactors, only about 0.1 kilowatts per person. Basically nothing.
But then comes the technological twist, the potential game changer.
Yes, this is where the numbers suddenly explode, but it relies on technologies that are, shall we say, currently unfashionable or underdeveloped. It's the combination of fast breeder reactors and extracting uranium from seawater.
Okay, explain fast breeders. How are they different?
They're much, much more efficient. Standard reactors mainly burn a rare isotope, uranium-235. Fast breeders can use neutrons to convert the much more abundant uranium-238 isotope into plutonium, which is also fuel. This process breeds more fuel than it consumes initially and unlocks about 60 times more energy from the same amount of natural uranium.
60 times more efficient. And the ocean uranium part.
There are billions of tons of uranium dissolved naturally in the oceans. It's very dilute. But the total amount is vast enough to power civilization for geological timescales if we could extract it.
So combine the 60x efficiency of breeders with this near-limitless ocean fuel source.
And the potential power output becomes colossal. MacKay calculated it could provide 420 kilowatt per person.
420.
Yep. That's the first number we've seen on the production side that completely blows away the 200 kilowatt consumption figure. Suddenly, the cost of fuel becomes almost irrelevant. The challenge is entirely about building, operating, and decommissioning potentially thousands of these advanced reactors safely.
It's a physics solution, a numbers solution, but it relies on two big ifs, making fast reactors work safely and economically at scale, and developing the tech to get uranium from seawater efficiently.
Precisely. It's the ultimate backstop in the numbers, but a controversial one. And just to round off the list, there's geothermal.
Right. Heat from the earth.
In places like the UK, which aren't volcanically active hotspots, the potential for sustainable geothermal energy is quite limited. Maybe 2 kilowatt per person at most.
Okay, let's try and balance the books. We've got consumption around 200 kilowatt sheet. And on the production side, if we add up all the plausible, ambitious, renewable contributions, onshore wind, 20, shallow offshore, 16, solar thermal, 10, tide, 14, wave, 4, maybe a bit of hydro and biomass.
Even being generous, adding all those maximum plausible renewable figures together, you're struggling to get much past, maybe 70 or 80 kilowatt reliably. You're still massively short of the 200 target.
The picture's pretty bleak, isn't it?
It's stark. The only way the indigenous numbers start to look potentially workable is if you include those huge, difficult, maybe implausible chunks like deep offshore wind, another 32, or covering 10% of the country in PV 50, or going all in on energy crops, 24. And even then, if just one of those big bets doesn't pay off,
the whole production stack just collapses, leaving you way below consumption. There's basically no margin for error.
None at all. And this leads directly to MacKay's absolute crucial point, the one that cuts through the usual political arguments.
Which is?
The debate should not be, should we have wind or nuclear?
Right. Because the numbers show.
The numbers show we probably need everything we can possibly get. All the plausible wind, all the plausible solar, all the tidal, maybe all the nuclear too. And even then, we still need to make huge cuts to our consumption. Choosing between renewables and nuclear is a false dichotomy when the reality is we likely need both, flat out.
Okay. And a big part of why relying solely on those renewables is so hard is intermittency. Wind doesn't always blow, sun doesn't always shine, which means you need storage.
Massive amounts of storage. MacKay looked at what it would take just to cover a typical 2-day lull in wind power across the UK. The storage needed about 480 gigawatt hours, GWH.
That sounds enormous, but it's hard to grasp. How did he put that into perspective?
He compared it to Dinerwig, the UK's big pumped hydro storage facility in Wales. It's huge, built inside a mountain. Dinerwig can store about 10 gigawatt each.
Okay, so 480 gigawatt.
It means you'd need to build the equivalent of 50 Dinerwigs, 50 giant underground reservoirs and power stations, just to provide a 2-day backup for wind power.
50 Dinerwigs. That really gives you a sense of the monumental engineering scale involved in making intermittent renewables reliable.
It really does. But storage isn't only about building huge new dams. MacKay also talked about dynamic demand, using our existing devices more cleverly.
Right, using things like fridges to help balance the grid. How does that work?
It's quite clever. The frequency of the electricity grid, 50 hertz in the UK, fluctuates slightly depending on the balance of supply and demand. Too much supply, frequency goes up a tiny bit. Too much demand, it drops a tiny bit.
Yeah.
You can build smarts into appliances like fridges or freezers so they monitor this frequency. If the frequency dips, indicating stress on the grid, the fridge could automatically delay its cooling cycle for a few minutes or slightly adjust its target temperature.
Just a small tweak for each fridge, but across millions of them.
The collective impact could be surprisingly big. MacKay estimated that if you could get all 30 million fridges and freezers in the UK to respond like this, you could potentially adjust demand by about 540 megawatts, MW, almost instantly.
How does that compare to grid fluctuations?
It's nearly enough to handle those huge surges you get during, say, the ad break in a really popular TV show, when millions of people suddenly boil kettles at once. Those TV pickups can cause demand spikes of 600, 800 milligW. So dynamic demand could be a really useful tool for short-term balancing.
Interesting. So looking at the big picture again, we need massive emissions cuts, like 70–85% by 2050, under that contraction and convergence idea.
Yeah.
MacKay was really clear that small incremental changes aren't going to cut it.
Yeah, he called the every little helps approach. Forget the phone chargers. We need to focus on the huge slices of the pie.
Especially transport, that 40 kilowatt for cars.
Exactly. We need a major shift away from single-occupant fossil fuel cars.
What's the efficient alternative numerically?
Well, public transport, when it's well used. A full high-speed train, for example, uses only about 3.3 kilowatt per 100 seat kilometers. That's drastically less energy per person than driving alone. It's about fundamental shifts in infrastructure and lifestyle, not just marginal tweaks.
And making these huge shifts happen requires policy. MacKay identified a core problem.
The fact that we don't properly price carbon pollution, it's too cheap to emit CO2.
Right. So big long-term investments like fitting power plants with carbon capture and storage, CCS.
They just don't happen or happen too slowly because companies can't be sure that it will be financially worthwhile over the decades-long lifespan of the equipment. There's no long-term certainty.
So the policy solution needed is
a clear, credible, long-term price on carbon. High enough to make a difference, experts often talk about something like $100 per ton of CO2 and guaranteed by government so investors can plan.
That certainty would then drive investments, like making sure all coal plants get CCS.
Exactly. Or incentivize switching to lower carbon fuels or investing in efficiency. Without that strong price signal, everything else is pushing water uphill. He also talked about shifting taxes.
The green taxes idea.
Yeah, basically pay as you burn, taxing pollution and resource depletion instead of taxing things we want more of, like jobs and income, shifting the tax base to align with sustainability goals.
Okay. Finally, we need to talk about the cost of all this, because building 50 Dinerwigs or a fleet of breeder reactors sounds expensive.
Extremely expensive. We're talking billions, probably hundreds of billions over decades. But MacKay puts it in perspective.
Oh.
He points out things like the UK's total annual spending on energy is already around $75 billion per year, and the estimated cost just to decommission the existing old nuclear power stations is about $70 billion.
Okay. So the cost of the transition, while huge, needs to be compared to other huge national expenditures we already undertake or face.
Precisely. Investing in new energy infrastructure, whether it's massive offshore wind farms or advanced nuclear or nationwide insulation programs, needs to be seen on that scale. It's a national project comparable to building the motorways or shifting the entire economy in wartime. It's not just a minor budget item.
It frames the financial commitment required if we're actually serious about making the numbers add up. So Wrapping up David MacKay's sustainable energy without the lot air. The main takeaway really is the power of those stark numbers. He showed very clearly that sustaining our current affluent lifestyles just using sustainable energy sources within a densely populated country like the UK is, well, it's an immense challenge.
Yeah, the numbers are really sobering. His analysis suggests that indigenous renewables alone, even scaled up incredibly ambitiously, likely fall far short of our roughly 200 kilowatt consumption.
Which means the conclusion isn't about picking winners between, say, wind and nuclear. It's that we likely need everything, all the renewables we can build, probably advanced nuclear too, massive gains in efficiency.
And significant changes to our consumption patterns, especially those really energy-hungry parts like flying frequently and relying so heavily on private cars. The numbers just don't add up without tackling both supply and demand head-on.
And the ultimate goal driving this, that idea of contraction and convergence for global climate stability, means aiming for something like 1 ton of CO2 per person per year by 2050, down from maybe 10 tons today in developed countries.
Which, as MacKay bluntly put it, basically means no more fossil fuels. Full stop.
So perhaps the final thought to leave everyone mulling over is this. If indigenous renewables have hard limits due to land and density, and our consumption is so high, what is the most realistic and ethically sound path to that no fossil fuels future?
Does the arithmetic force us into radical lifestyle changes, maybe severely limiting flying and driving? Or does the scale of the challenge inevitably push us towards relying on either importing vast amounts of energy, perhaps solar power from deserts overseas, or embracing those large-scale, centralized, but currently controversial technologies like fast breeder reactors using ocean uranium?
It's the numbers that really force you to confront those difficult trade-offs. There aren't easy answers once you look past the adjective. We really encourage everyone to try and apply that number, not adjectives mindset, to energy discussions you hear. Thanks for joining us.